हेलो स्टूडेंट्स, कैसे हो आप सब। आइए आज हम लोग मैग्नेटिक इफेक्ट्स ऑफ करंट में लेक्चर 6 आज हम लोग करने वाले हैं एम्पियर सर्किटल लॉ। इन द लास्ट सेशन वी हैड डन Biot-Savart law, right? An application of all applications of BS law, right? Now we will do Ampere Circuital law. This is another method to find out magnetic field, but this is due to the magnetic field of not, suppose you have a cylindrical wire, right? Wire of this thickness, some significant thickness is there, and with a thickness inside the wire, if you need to find out magnetic field, then this tool will be applicable. Which tool? Ampere Circuital law. So first of all, understand what is it, and then we will explore where we can use Ampere Circuital law. Okay, so very basic idea we have that a long cylindrical long straight conductor carrying current has magnetic field around it. You are aware of this. Okay, so the direction of magnetic field is given by what? Curl of the finger. If thumb represents the direction of current, then the curl of the finger will represent the direction of magnetic field. This is what we have understood. As you know that there would be multiple concentric circular loop of magnetic field, right? Multiple loops. There would be multiple concentric magnetic loop. So if you take this loop, suppose this loop we have considered, this is the loop of magnetic field, this is the current flowing in this conductor, then this law is very simple. Line integral of the magnetic field around an enclosed loop is equal to mu naught times the total current enclosed by the loop. Okay, what is it? Line integral. When we say line integral, what do we mean by that? Dot product of magnetic field and length of the loop. Dot product of magnetic field and length of the loop, right? This equals mu naught times the current enclosed by the loop, right? So here, if we consider that magnetic field, the loop of this magnetic field is of radius r. Loop of this magnetic field is of radius r. Then we have to consider that, okay, this loop is enclosing the current I. Okay, so this we have to understand, right? So mu naught into I. So if there would be multiple, if this loop encloses multiple currents, then what will happen? Add them all. Okay, I give you the example. Let us understand this. This was the statement of the law, Ampere Circuital law. This is very simple to understand, that this is what we call it line integral of magnetic field. That means dot product of magnetic field and the length of the loop, right? This is equal to mu naught times the current. Okay, now what we are supposed to do, we have to understand how this law can be proved. Okay, so let us understand how this law can be proved. Okay, so proof of ACL, that is Ampere Circuital law. This one is very simple. Be very attentive, you would enjoy it. Okay, so you have one long straight wire, long straight conductor or wire, whatever you say, So magnetic field due to long straight conductor carrying current is equal to what? B equals mu naught I by 2 pi A. We are aware of this. So this we may say 2 pi R if you have taken this distance, right? R is the loop. Just try to understand what is it. We have this current, long straight current, right? And magnetic field, let me put another, this is magnetic field. This is magnetic field. Okay? This loop in the brown, you may consider it to be the magnetic field. This is magnetic field. Okay, so what we have taken, this is the radius. R is the radius. So this is the wire and this is the loop. Loop has got radius R. This is the loop of magnetic field. Okay, one thing. Second thing, what is the radius of that loop? Radius is R. Okay, this is the distance. This is also the distance where we are finding out the magnetic field from this wire. Is that okay? So magnetic field due to straight wire is this, right? Now what we will do? Mark this equation 1. Now line integral we will find out. Line integral of the loop, right? Line integral. So B dot dl. So if you have this, it means for the entire loop, closed loop, So this can be written as B dl cos 0 degree. One thing. Here, this one is also very important. If we have taken this loop, you may say this, at the loop, every point inside on the loop, at every point, magnetic field will be constant. So this will be constant. That is quite simple, no? At R, if R is fixed, then magnetic field is going to be fixed because current is not changing. So at every point on the loop, magnetic field is constant and the magnitude is this. This you have understood. Now, one thing. Second thing, the loop, the element of the loop is also, let me mark it here, the element of the loop dl. So element of the loop has got this direction. Okay? The direction of magnetic field. So there is no problem considering this B dl cos 0 degree. Okay? One thing. Second thing, if you are taking this for entire loop, then what it is going to be? If this is dl and this is your magnetic field, this we have understood. Now what? Now the entire loop, perimeter we will take into account. So for the entire loop, we have 0 to 2 pi r limits, right? 0 to 2 pi r limits. If you consider for the entire closed loop, it is going to be 0 to 2 pi r. So what we are going to get? B. So B is now constant. So B is constant. So B can be taken out of this integral sign. This B into dl. Cos 0 is 1, so no problem with this. 0 to 2 pi r. So what do we get? We have this equal to B into, it will be what? If you integrate this, you are going to get 2 pi r. Right? B into 2 pi r. So finally, we have got this. Now, what will happen? We have B dot dl for the entire closed loop equals B into 2 pi r. Substituting B equals mu naught I by 2 pi r from equation 1. From equation 1, you can you can see this. You can see this from equation 1. You have B equals mu naught I by 2 pi r. This was the magnetic field due to straight long conductor we have taken. Okay, so this will be what? This will be B dot dl for this equals, for B we will put mu naught I by 2 pi r into 2 pi r, and the final result we are getting is this. So B dot dl for the closed loop, this is your ACL, right? This is the proof of ACL. So quickly, if we wish to recap, just have a look. Magnetic field due to straight long conductor is this, mu naught I by 2 pi r. R is the distance from the wire, and that is the radius of the loop. Magnetic field, loop of magnetic field also. Okay, now we will take the line integral of the loop. Line integral will be dot product of magnetic field and dl element. Dl element is of magnetic field itself. That's why the direction will be in this. Both will have same direction, magnetic field and dl element. Okay. Now what? B dot dl into cos 0 degree. That is quite simple, because they are in the same direction. Okay, and what would be the limit for the entire loop? For the entire loop, limits will be from 0 to 2 pi r, the perimeter. Okay, that we have taken. Now what will be there? B is constant, as we have understood this. B is constant and we have taken it out of this. So finally it is coming out to be B into 2 pi r. Further, if you go into this, B dot dl equals B into 2 pi r. Substituting the value of B, we will get this result. Okay, hence it is proved. Now what we are actually going to do, we have to understand very quickly why this special tool is needed. Why another tool? We have one tool of BS law, BO-Savart law, to find out the magnetic field, right? So how this one is different from that? We have already done BO-Savart law, right? BS law, and we have found magnetic field due to various system, various type of current, circular current, straight current, square loop. There are so many loops we talked about. Now why this is going to be so important? So let us discuss where we are going to do this. We are going to use this result. So magnetic field due to current, which current? That is also important. Which current? Straight long conductor carrying current. Okay, so how this is so important? We had already done this, but one thing we could not do, that if we need to find out, suppose we have this thickness of the wire. Try to understand this very, very simple thing. This thickness of the wire. So while applying BS law, we did not talk about the thickness. If we wish to find out the magnetic field inside the loop, let's consider this. If you have loop inside this, so if current is flowing this in this entire cross section, try to understand this. Current is flowing in this entire cross section. I, if this we have taken, this is I, for this entire cross section, if current flowing is I, then do you think that same current will be flowing through this cross section? No. For this cross section, the current flowing would be different. Current flowing would be different. Understood? For this cross section, current flowing will be, amount of current flowing would be different. So this is where this law is applicable. We can easily find out magnetic field due to this current. This is long straight conductor, you know, this is long straight conductor, and the current flowing is, for the entire one, current is flowing I, but for this cross section, current flowing would be I dash. Try to understand this very fact. Not the entire amount of current will be flowing through this. So if you have to find out magnetic field, at this point, okay, which is r distance, which is having r radius, which has radius r, and this has got radius, this is a, okay. So this we need to understand. This law, which law? ACL law is applicable in this. BS law we cannot use here. Okay, now let us find out how to find out the magnetic field. So first is case 1, inside the conductor. Magnetic field, we are finding out magnetic field inside the conductor. Inside the conductor means what? This R is less than A. So first of all, write down what is A. A is radius of cross section of the wire. Okay. And what is R? R is the radius of, we call this Amperian loop. Amperian loop means the magnetic loop which encloses some current. Okay, so that we have taken Amperian loop. Okay, now the amount of current, first of all we need to find out, we need to put here the current, amount of current enclosed by the loop will be I dash equals I by pi a square into pi r square. Be very, very clear about this. Because we have to talk about for the entire cross section, current flowing is I. So for this cross section, what would be the current flowing? So this cross section has the radius r, right? This cross section has radius r. This is r. Okay. So current per unit area into area of this cross section, right? Why this cross section is so important? Because we are supposed to find out magnetic field at this point, right? Which has got a distance from the center of this, from this center. What is the distance? From the center, this, this loop has got radius r. So this is what we need to understand. So pi r square, area of this cross section. So because entire current will not be flowing through this cross section, that we need to understand. So area per unit, current per unit area into area of this loop. Okay, area of this loop, area of this cross section. So now what will be there? The final result will be I dash equals what? This pi gets cancelled, I r square by a square. Okay, Why this one is so important? Because we need to use this concept. What? So now let us take the loop, magnetic loop. B dot dl should be mu naught I dash, applying what? Applying ACL. So B dot dl equals mu naught into I dash. Here it would be there. This has to be applied, right? Because this we need to find out. This is the current. This is the current enclosed by this loop. Okay. So we have B into 2 pi r equals mu naught I into r square by a square. Okay. So what is the final result? B equals mu naught I by 2 pi a square into r. So this is going to be the result. This is inside. Okay. Now case 2. Case 2. Outside the loop, outside the conductor, outside the conductor. So in this, what we are going to do? We have this wire. We have this wire and this cross section. We have taken the loop to be. We have taken the loop to be this. This loop. So this is now here. This is of radius r again. So here in this we will say r is greater than a. So whatever current is flowing in the entire cross section of the wire, that will be accounted here. Okay. So here the current flowing will be I for the entire cross section, because this entire cross section is being enclosed by this loop, right? Okay. So what is going to be? Again, use this B into 2 pi r equals mu naught I. So ultimately this B equals what? Mu naught I by 2 pi, mu naught I by 2 pi r. So this is for the outside one. Okay. So if you plot it, if you think of it, inside the conductor, how it is going to be, and outside the conductor, how it is going to be. This question was asked in Neet 2019. Okay. So this is very important. B, and this is in NCRT also. NCRT example. So very popular question. How this magnetic field is changing with distance. At the center of the cross section, at the center of the wire, right here, it is going to be 0. As you move further from the center to the surface of this wire, it is going to be increasing. Why so? Look at this. Here. Look at this. Here, B inside is directly proportional to R, and here B outside is directly inversely proportional to R. And this is the expression which we found using BS law. Right? This is the expression we found using BS law. Right? Okay. So this is only possible, this expression is only possible using ACL. We cannot get this result using BS law. So that is where ACL is so important. I hope you have understood this. Okay. So this we understood. Now how the graph will be plotted, just have a look. From the center, if you move towards, it is directly proportional. Move towards the surface, right? It is increasing. So if it is increasing here, there is dotted one. I have taken this. So this is R equals A. Beyond this, if you increase the value, till here, magnetic field is increasing. Beyond this, it is decreasing. It is decreasing. Right? Like this. So what is the B inside? It is directly proportional. B outside, it is inversely proportional to R. This is how this graph is going to be. Okay, so what is ACL? What is the proof of ACL? Where ACL is significant, right? And where Bayes' law is significant. Actually, this can be found using this magnetic field due to straight long conductor can be found using ACL also, using Bayes' law also. But only for the outside point. Be very clear about it. Only for the outside point. Right? For Bayes' law is applicable when you are not considering the thickness of the conductor. If you consider the thickness of the conductor, in the entire thickness, in the entire cross section, some current is flowing. So if you are interested in finding out the portion, the loop inside, the portion inside the conductor with smaller cross section, so in that case, ACL is applicable. So this is going to be there. Okay? So this was the basic idea behind this ACL, Ampere Circuital Law. If I simply ask you to find out the magnetic field due to straight long conductor using ACL. Okay, that you can do for outside point. This is going to be the result. But inside the point, during using ACL, this you need to be very clear about. You need to find out first of all the current enclosed by the loop of this cross section. You can view it here. Okay, and then you will find out the magnetic field due to this. Because applying what ACL, you will say that okay, B dot dl equals mu naught I dash. In this case, current enclosed will be this. Less amount of current will be flowing through this cross section. So that is significant. Okay, and yes, graph is also very important. Magnetic field versus distance. This is very, very important graph. Now let us understand the application of ACL law further. Two applications so far we have to do as solenoid and toroidal solenoid. Solenoid and toroid. Okay, solenoid and toroid. So just have a look. What is this? This is only long straight conductor. So these are the loops of magnetic field, as you can see. Okay. Close to this conductor, close to this straight conductor, you see magnetic field lines are quite, closer. And now this is solenoid. What is solenoid? This is, wire of multiple turns. Okay. Current is flowing and magnetic current is flowing in this direction. In this direction, and magnetic field is in this direction. Right? So this here, current is flowing like this, magnetic field is like this. So in the next session, we will derive the magnetic field due to solenoid, and that is going to be B equals mu naught Ni. N is what? N is number of turns per unit length. So we will talk about this in the next session, and we will derive this solenoid and toroid properly. A magnetic field due to solenoid and toroid. Okay. So whatever we have done till now, you need to properly practice. Okay. So that this application can be easier for you. All right. See you in the next session. Thank you.